Welcome everybody to today's webinar. This is Fred Schenkelberg, and today we're going to talk about a little bit about tolerance analysis. And I did mention this in the last webinar as one of the uses for Monte Carlo analysis, and we'll touch on it a little bit more. Before I move off of this screen, I wanted to mention here's a link in the lower right hand side in what's called the links pod, where you can find a recording of the webinar last month, which goes into much more detail about how to do Monte Carlo analysis, which we just won't have time for today. After thinking about it, I probably should have done this webinar before I did the Monte Carlo one, but so it is. There's also a free ebook. You just need to be a member or signed in to need to be signed in to the Ascendo site as a free member, and then you can download the statistical tolerance analysis ebook, which goes over pretty much everything we're going to talk about today and a bit more. And Carl, thanks for the sound is good. The handout, if you're talking about the slides, you need Adobe Acrobat Reader, like either the most current version or close to the most current version to view it. And I believe there's a few other readers that do work with it, but not all of them do. It's created in a funky way using some Adobe software, which works great for presenting, but not all that great to the presentation. And if it's still not working, send me an email and you can get it from me that way.
Pardon me, is there a way to get a link to your screen?
A link to the screen.
There should be a link in my invite for your screen.
Oh, well, let's see what I can do. Well, send me an email and I'll send you the link, because you should have gotten it with the invite.
Yeah, I will do that.
Okay. All right, sorry about that. Let's move over to the presentation side. And I should also mention one more housekeeping thing. If you are dialing in on the phone, not over voice over IP, please mute your line so we don't get any of the background stuff. That much appreciate that. All right. Today's presentation is on the fundamentals of tolerance analysis, and it's just an intro to this. And tolerance analysis is a technique during the design process of understanding and accommodating the range of variability that occurs in manufactured parts. And the design team oftentimes will set tolerances or specifications of what they want, and when it's done well, it accommodates or accounts for the expected amount of variability of the components and materials that they're using. Now, it's done in a number of different ways, and we'll talk about that here in a few minutes, but it's not a hard science of how it's done, and it ranges about as many different ways as I've seen engineers actually set tolerances. And there's better ways than others. Yet it does tie in to what we do as reliability and quality professionals, or folks trying to create a reliable product. Now, as you know, and if anybody, I know Mike has listened to a few of my presentations, but it's a variation happens, right? It's out there. Things change, things vary. We rarely, if ever, make two things the same twice in a row or twice ever. So it's part of the world that we deal with that we have to have, that variation exists, and it's something that we're just going to have to deal with. So in the design process, this ability to accommodate the variability, or at least to acknowledge that variability, is often done through tolerance analysis. And it's a process of taking either an educated guess or doing some analysis or some study or some measurements to understand what the variation is expected to be, and then incorporate that into the design to see if the design still works. And so I'm using railroad tracks for today's series of slides, and it's a standard gauge. Now, every railroad axle is not exactly the same width, right? But that's accounted for in the design of the system so that many different manufacturers can make rolling stock that fits on the many different constructions of railroads. And by and large, it pretty much just works. And so that's one of the ways that tolerance analysis affects the things that we do, is that it allows us to make things not perfectly, and it still works. Now, reliability fits into this because variation happens. And if we create a design that has to be perfect in order for it to function well and to function well over time, well, then we're going to have failures because, again, variation will happen. The other part is and we talked about it a couple of webinars ago when we were talking about weather data, for example, is that varies. The stresses in general vary on our products. And so in part of what we do in the design process is account for the changes of materials and the changes of dimensions over time, right? Materials shrink or swell and under different sets of stresses, or they wear or so on. And will that product still work? And so in part, that's part of tolerance analysis. But so there's really two ways that tolerances, when done improperly, can lead to failures by not accounting for the true range of variability that occurs in the manufacturing of our products, or in the changes in the product as it ages or it undergoes different stresses. Now, if either of those goes outside of a range where the product or the system fails to function, well, then that's a failure. That's a problem. That's a lack of reliability. And so hopefully with that simple, and I understand it's a simple view, but it's a way to look at how important tolerancing is to the reliability performance of your product, right? And so that connection to me is very real. All right. So, but what's our role, right? We typically don't do the tolerance analysis, but what do? What's our role? What do you think is the best way to deal with this? How do we get involved with this? Oh, thanks, Michael, for the outstanding presentation. Unless you're talking about the few that were not done by me, which is great because there's a bunch of really good ones there too. Michael, the tolerance analysis is often not a part of the quality engineer's role, right? They have a function of looking at stable processes, and is the process in control? Are we getting a steady, consistent output of, say, a dimension of a bolt, for example, or from a supplier? But they feed that information into the tolerance analysis. Yeah, they might do, and we might do, checking or validating these things. That's a good part. Yeah, Rohit, there's a piece we have in there. Yeah, modeling and statistical analysis. Yeah, there's some of that too, Micah. I go a little bit deeper than that, and let me explain. Let's see. Let me go back to the question here. I think our role goes all the way from material selection and design architecture, which significantly impacts the reliability of the ensuing system. We also work with mechanical engineers, electrical engineers, and others to understand where the critical to reliability elements of our product and systems are. And then as the engineering teams put pen to paper basically, or pixel to screen, to create a design, it becomes this dialogue of what's the critical elements of the system. What are the areas that have the least margin, which have the most unknowns, which ones are most critical to the proper functioning of the product, such that if they are not in spec or not in the proper dimensions, will they still work, right? So all of those elements are pieces of what we can influence and what we can contribute to the engineering team. Now, the other piece of this is that reliability engineers often have a wide span of control and visibility of the entire supply chain and manufacturing process and design process. And so identifying those areas where we need better data, where we need better control and stability of our processes, the SPC elements of it, we can influence or actually manage those pieces. Bringing that data back to the design team such that they can improve their ability to do the analysis, the tolerance analysis, allows them to make better decisions. Now, they don't always have the access to the data and the visibility that we have. In some teams, certainly they do, but not all teams. We can bridge these different parts of our organization to make sure that the right sets of information are in place so that we get a good set of tolerances that enhance the ability of the product or system to function. And so those are all essential elements to creating a reliable product. Now, as a product is designed and tolerances are set, we have a monitoring role. Is this working, right? Are the failures we're seeing signals that we're experiencing variability that's greater than what we expected in the tolerance analysis, right? Did we get it right the first time? If we assume things would be in spec, but they're not, that may lead to failure. Now, part of it is the supplier providing the right parts, or is our manufacturing process stable? Is it in control? And did we account for the natural range of variability that's occurring? Not the expected, not the specified. There's a huge difference between a specification and how much the variability, what range of actual variability you get. Anybody that's worked with any kind of product or system understands that. What we specify is not always what we get. And so tolerance analysis is aimed not at the specifications, it's aimed at the actual variability. And so bringing that to the mix is one of our roles in the ability to create a robust design that can be built with the variability that we're going to see, which enhances the reliability, right? Okay, so there's 3 different methods that I commonly see out there. And one of them is called worst case method. I'm sure quite a few of you have heard of this and have actually used it. It's easy, right? You just kind of add up the absolute worst ranges of values and see what you get. It's simple summation. It's conservative, and it's a great tool that many people start with or use initially, because if it works under worst case analysis, there's really not a lot of reasons. Working mean it's reliable and the design functions. If it works under worst case, there's rarely a need to go further, right? Now, that doesn't always happen, that it works when you're at the extremes of your parts, and so we may explore other methods. And sometimes the design, you just can't assemble it if you're at the absolute worst case of situation. So I'll show that in an example. Okay. It's easy, right? You take the nominal values, you add the minimums, and you add the maximums, and you see what you got. And some cases you need in order for it to be the worst stack up of dimensions, you need the minimum of this and the maximum of that, for example. And more often you see that in electronics. But some mechanical systems have that realm. So it's a little bit of thinking through how the design interacts and how the parts align and all those pieces to figure out what's the worst sequence of values to cause a misalignment, for example, or a excessive wear, or whatever it is that the lack of tolerance provides. And so, but it's simple math, right? It's just add it up, think it through a little bit, pick your worst situation, tally it up. You get a real simple number. So let's use just a quick example. Let's say I've got two plates, and essentially what I want to do is fit them into a tray, for example, or a slot or something like that. And let's see if I get my drawing thing here. All right, so let's say I've got two plates, and I'll just draw the ends of them here and show that they're not quite touching, but let's say they're mating as close as they can. And each one's about 20 millimeters thick, and plus or minus 1 millimeter is the range of values that we would see. Right? So if I want to find out what's the maximum thickness of the stack up, and it's 2 times the 20, or add up 20 millimeters twice, which gives me the nominal thickness. And then I got 2 1 millimeter thicknesses to add to the top, so 22 millimeters, right? And if that fits in the opening I'm looking for, then it'll always fit. Now, sometimes I want it to fit snugly, or I want it to fit appropriately, but not too loose, right? I may have a specification on that. So then I use the minus side on here, and I get, with a little quick math, 18 millimeters thickness, right? If I happen to pick the 2 thinnest in the group, trying to draw an M here, oh, yeah, 42 and 38. Thanks for catching that, Rohit. Now, the next one will be a little harder to do math, and I should have worked these out prior, but you get the idea. Even simple math, and talking live and trying to draw at the same time doesn't always work. All right, yeah, 42 and 38. Now, if my opening can accommodate that range of widths, and if this plus or minus 1 millimeter actually encompasses the full range of variability, right? That's a big if. Now, if I went out and did a bunch of measurements, and I know that my min and maxes are at this limit or better, then I'm probably good, right? Now, sometimes, though, I may have a specification that I need to be within, say, 41 and 39, right, instead of this range here. So now I'm going to have some that won't fit by chance. Wow, handwriting's really bad, right? And so worst case example doesn't really give me a lot of information about whether or not it will, what proportion, what percentage will work or not, right? It just gives me a yes, no. Will this fit my criteria or not? Now, it's compared to what is the design team specifications. What are they looking for in order for the system to be considered working or operational? And if worst case allows you to do a quick calculation and the design team is saying, yep, that'll work, then you answer the question, you move on. You go find something else that's more critical. Now, the hard part is that when it's close, when it's on the edge, or when it doesn't quite work all the time, we often will say, and I've heard this from designers, is, well, the chance of getting 2 plates that are both at the absolute minimum dimensions or at the maximum dimensions is pretty rare. Now, that's true, but what proportion? And what proportion of failures can we accept that will occur? right? And how close is close enough that it won't happen. And so the worst case example doesn't give us enough information to do that calculation. So it's a good first pass. It's a good, and you see it very commonly done by, and I can think of a dozen of different mechanical engineers that's standard practice for them. They just run the worst case and see if it's still got the clearance, if it's still got the fit, if it's still got the alignment, and then they move forward. Yet when it's close or it's critical, it's not going to give us enough information to really understand what's going on here, right? But it is a common technique, and I wanted to quickly explain it, even with my bad on-the-fly math. And I even thought of that yesterday when I was putting this all together and practicing it, and didn't make the notes to do the calculation. So thanks for keeping me honest there. All right, so when is it appropriate? When should people do worst case analysis? And I tried to answer a little bit of the question of when not to do it, is when it's a critical part or when you need to know what proportion would be in the specification or not. Yeah, when the risk is high. Yeah, perfect. So, Al, I'm not sure I know what you mean by parts versus few parts. This is when you have a lot of things in the stack up. Now, I've run into where even getting an alignment for an attachment, we're trying to attach a circuit board into a frame, and on the two ends of the circuit board, we're mechanically through many different components. And so there was a good number of components that made the alignment very, very difficult. So yeah, the more complicated a system, the more difficult it is. In worst case makes it's just adding the worst situation. So getting an alignment, say if you're trying to align two plates two-dimensionally and get a hole lined up, if you're trying to align 6 plates, it's much more difficult given the variability just adds to each other and makes it worse and worse and worse. So one solution is make great big huge holes and use a very large headed bolt to accommodate that variability, but that also weakens the joint. And so it almost always a set of engineering trade-offs, and tolerancing, when you know the actual variability, enhances that ability to make good trade-offs and good decisions. So root sum squared method. This is the next method, and it's not terribly difficult. It uses just a touch of statistics, not too much, yet it accounts for that probability that we're not going to get always the worst parts stacking up together or always the best parts stacking up together, right? Yeah, Joe, exactly right. It's the more dimensions of the fit, the more complicated it can be. So the root sum squared, it's really using the standard deviations, right, or the variances, I should say, of the part variation. Now, the hard part here, and really the only hard part, is we need that data, right? We need to estimate the standard deviations, or we need to estimate the variance of the variability of the components we're dealing with. Now, that can be a wide range of estimates. It can be from straight out guess, taking a data sheet saying, well, here's their specification, and we'll say that they're going to be within that range, and call that a plus or minus 3 standard deviation. And we can take that range and divide it by 6 and come up with standard deviation. Or if we want to be conservative, we can say, well, they might go out of range sometimes, so we'll do the standard deviation is that spec divided by 4. But those are just guesses, right? Those, without hard knowledge of those measurements, it's really just an estimate. Remember that specifications are oftentimes just a hope or a wish. They may reflect actual data. This is what their actual process does. And oftentimes that assumes that the process is stable. And this is from the statistical process control and process capability realm. So if I've got a specification and I know that the process is stable and has a capability index of process capability index of 1, that implies that they are centered and plus or minus, or not, CPK, I should say, assumes then that if 1 would say that we're centered, and that the variability at plus and minus 3 standard deviations from the mean just touch the outer, the specifications, right? So if we know that information, the supplier has given us SPC data and our quality folks are calculating capability indices, we could back out what's the standard deviation for the variability of this part. Now, of course, we would love to have capability indices that are 2 and greater, meaning that we're well away from the specifications and it's much, much tighter. And so if you have that data, if you've managed to track down and verify that it's accurate data and that they truly do have a stable process, we get much better results from a root sum squared calculation. And the benefit is that it accounts for the randomness of selecting parts. Now, the downside is that it assumes a normal distribution for everything, right? It's just straight out assumptions. As soon as I take a bunch of standard deviations and tally them up using, remember you got to tally variances, not standard deviations, and then take square root of that to get the system or the stack up standard deviation. If we have good understanding of the variability as a standard deviation and the variability, it can be described as a normal distribution, the classic bell-shaped curve, this works great, right? It's quick, it's easy, we do some simple calculations. The hardest part will be getting the data, understanding our processes are stable. Oh, say, Carl, yeah, I think I can put the, let me grab the link. Now, do you mean the presentation, Carl, or the slide deck itself? Because here's the presentation window. Slide deck, all right. Well, I don't have the slide deck online as a separate link right now. I will once I get the video posted, so I'll go with that once I get it there. And it'll be a couple of days and it'll be up on Ascendo Reliability /webinars. It'll be in that area. But I'll track it down and get it linked to that once I get a chance. And I'm getting a bunch of people requesting to join the room, so I'll go ahead and take care of that while I'm on the site here. But we'll get it posted, Carl. All right. So root sum squared is easy. It's not quite as easy as worst case, but if I'm a true normal distribution, right, most of my parts are going to be within that plus or minus 1 standard deviation. And, you know, that's fine. That works great if they really are a normal distribution. Now, some vendors will sell you parts that they sell the very tight tolerance ones. They separate those out and charge you more for it, right? So you don't get the middle part. So most of your parts are going to be outside of that first standard deviation. And that can be a problem, right? So it's for the critical parts, for the essential pieces of stuff, if you want to use root sum squared, is get a gauge and go measure it, right? Do the gauge R&R, make sure you got to minimize your measurement error, and go make the measurements. And see what distribution you really have, and see what range of variability you really have. And that is easier said than done, right? Yet for those critical parts that are really going to impact the performance, the assembly, and the reliability of your product, it's worth doing to really get the data to understand what's going on. Sometimes that's possible, sometimes it's not. The design is coming first, and you've got to create a estimate before the design is manufactured. Now, in those cases, what do you do? Where do you get your data if you haven't created the components yet to even make the measurements? In the cost of creating those first prototypes, it may be expensive. So it's one of those where I can't get there until I already have the parts, and then it's too late. So what's a technique to deal with that? Let's say I'm machining a part and I haven't made it yet, so I don't know what variability that part's going to have. What's the option that you have to get an estimate of variability? Well, one that comes to mind is that process, that machining process, whether it's stamping or forging or milling, is that process probably has a range of variability for different types of cuts or formations of a part. Now, it may not be exactly your part that's coming out of it, yet the range of variability for that process may be well understood by the manufacturer. And so at least measure parts that are similar to yours or from the same process. What's the types of, say, surface roughness or dimensional variation that naturally occurs from that process? Now, mechanical engineers often understand that different fabrication processes come with different tolerances and different ranges of variability, and also different finishes and different ways that they result in the final product. And so that often can be to be taken into account when you're creating your first estimate. So a little bit of creativity sometimes goes a long way to understanding the variability initial estimates, right? Now, another piece of this is that we're also assuming, besides the normal distribution, is that we're often assuming that it's a stable, in-control process, right? So we may go off and make some measurements, and one of the assumptions is that when we ramp up production and we bring on more manufacturing lines, that variability will stay true. Now, it almost never occurs. Variability almost always gets worse, or larger, I should say, which in my mind is worse. So it's even when you go make the measurements, if you know that your process is going to expand, it's going to have different sets of variables impacting that resulting variability, you can take that into account. Put a safety margin on your tolerance range of variability. It would be one way to go at it. So a couple of concerns there. But it's common. It accounts for that we're not always going to get the worst possible parts every single time. The other real benefit I like of root sum squared is that now we can estimate how many of these stack-ups, how many of these tolerance analysis, this stack-up analysis, is going to result in parts that are out of specification, that are bad, right? So if I have the variance of each of the components, I can tally these things, and I can have a resulting system standard deviation, and then calculate how many parts are going to be bad, given that we have variability, randomness essentially, of what the dimensions are of the assembled parts. And so it takes into that account, again, really assuming that we have a normal distribution for everything. Right? The hard part, as I mentioned, is getting the standard deviations. Right? It really does hinge on that you have an accurate description of the variability of your components, and the more normal they are, the better. right? That doesn't always hold true, and for critical things, you should check. But, and I mentioned this earlier, is we sum the variances. Anybody remember why we sum variances and don't just add up standard deviations directly? This may go back to your stats theory class that you may or may not have paid attention to. Yeah, variance equals the squared standard deviation. The variances are additive. Standard deviations are not. Right? Now it gets into a bit of theory as to why that occurs. I'm not too sure about that, Sean. Is that standard deviation going to be negative? It's hard to have a negative range of variability. I'll have to think about that. But anyway, the underlying notion is that in statistics we have means and variances, skewness and kurtosis. Those are the moments of a set of data, right? And we can manipulate those moments. But we can, obviously, we can square standard deviation. Now, we use standard deviation for lots and lots of things because it's in the same units as the mean, which is more convenient for many, many things that we do. Yet, we can mathematically manipulate variances. And there's a couple other ways to describe this, but keep in mind, it's a common mistake. If you just add standard deviations, you're not accounting for the mathematical combination of that set of variabilities. It really only manipulate variances. You can convert it back to standard deviation so it's in the right units for common understanding. But it's a basic process. The hard part, again, is getting the data for the standard deviations. And so on this one, I'm not going to try to run the math out, but I'll give you a quick example. Again, let's say we just have two plates that are each the 20 millimeters. Now, if I assume that I have a normal distribution that goes from 19 to 21 for each plate, most of my data is going to be pretty close to 20 millimeters in that plus or minus 1 standard deviation. Right? So most of my data is going to be that combination of those two things. Now, the combination of those two things is going to be a little bit wider, right? Because I've got the standard deviation of part 1 and plus the, or I should say the variances, and of part 2, oops, trying to draw too small of a thing here. Anyway, squared, and then square root of that. This tally will be a bit bigger of the system. The resulting standard deviation of the system will be a bit bigger than the individual variations. Now, of course, I don't have to use exactly the same distribution. If I'm putting two different parts together that have their own ranges of variability, their standard deviations obviously can be different. But the idea is that I'm accounting for the natural range of the variability, and I get a system variability if I'm assuming that they're all normally distributed. And then it works pretty well. Now, on the contrary, if these things are very skewed, for example, if the variability looks like that, or if the variability is bimodal, where somebody's taking out the ones that are close to 20 millimeters, I'll still be able to run a calculation, but it won't reflect what the actual variability is. So that's a significant assumption, and it's one worth checking if you have any doubts if that's occurring with your system, with your supply chain and suppliers and so on. And so to run a calculation like this is simply adding these standard deviations. We need to come up with a standard deviation. but heed the desire to go, oh, this plus or minus 1, that's the range of variability. I divide that by 4, divide it by 6, and I get a standard deviation, and off I run. Sometimes, right? Is it truly a specification? That's a wish. Or is that actually the range of the variability that you experience? And when it's important, go measure it. There you go, complex normal. Thanks, Ray. Yeah, there's a bunch of probability theory stuff that when I was doing my master's program that, yeah, we had to pay attention to it because we were doing homework and we had to understand it. But I was working in a factory at the time, and every day after class I'd go try to apply what I was learning. The theory didn't apply as well. Trying to explain it to my colleagues and peers didn't go very far. But when I was able to set up and run control charts and actually identify areas for improvement, that was really useful. And so I tended to pay way more attention to the practical side. All right, so when's our root sum squared appropriate, right? So Jason, the 2 equals 6 sigma, you're talking about the CP and CPK capability indices in that regard. Yeah, and I'll do a quick drawing how that relates. And I think I don't remember if I've got something on 6 sigma. That might be another good webinar. But let's say these are my specs, right? And if my variation at plus or minus 3 standard deviations, that's a bad drawing of a normal curve, just touches this and it's plus or minus 3, the CP, CPK values would be 1, right? Now, when we're talking about 6 sigma, is the variability is much, much tighter. Now, ideally that would be centered such that I have 6 standard deviations to both, at least 6 standard deviations to both specifications. Then our CPK will be 2 or better, right? It just means that I can move this quite a bit and I still stay within the specifications. And so if it's stable and centered and a CPK of 2, yeah, we can say that it has plus or minus 6 standard deviations between the mean and the specifications. Right? Lots of ifs there, and it's always a moving and changing environment, so it's something to be cautious about. So, oh, the example I demonstrated, plus or minus 2 and 1. Yeah, could be. All right, this next one I even get further away from an example because I did it, oops, get myself going, is Monte Carlo, because there's a whole presentation on that, and it's in the links tab, which is in the lower right hand side of the screen. I think it's still there. So Monte Carlo adds another level of complexity and accuracy. So for those things that are important, that the root sum squared, the set of assumptions that we make about being normal, or when we know it's not normally distributed, it has a range of different variables that are whatever distribution they are. Monte Carlo is the way to go, right? Because it can account for that statistical spread of the data in whatever form it takes: normal, log normal, Cauchy, skewed, exponential, whatever, bimodal, you name it, Monte Carlo can deal with it. And the idea is that adding that much more data, it takes time and expense, and you have to get the information, which is not always trivial, so it adds expense. Yet what you get out of it is a much more accurate tolerance analysis, right? Now, both root sum squared and Monte Carlo allow you to do this cost-benefit trade-off, right? Do I need to improve this component so that it has a tighter range of variability. Now that will cost us more to actually accomplish that, but is it worth it? Right? And sometimes it is. But it allows us to do what-if analysis. Both our RSS and Monte Carlo do that, allow us to do these kinds of trade-off analysis, but also help us identify what are the areas that are most critical to creating the system's variability. What are the significant contributors to that, and where do we need to focus our attention for that process improvement to reduce the variability, right? The advantage here, to some extent it's a disadvantage, is that we're not assuming a normal distribution. Yet we need to estimate what it is, right? So sometimes we use a uniform distribution, sometimes we use a triangle distribution if we just have a need to create an estimate and we need to pick something based on our experience. But sometimes we actually go make measurements and fit the appropriate distribution to it. But as with anything, when we've got good data, this can be very accurate, right? So Monte Carlo is a bit more overhead, a bit more work to accomplish. We get deeper into the statistics of different distributions. We have to use a computer system to run the Monte Carlo, the simulation that it exists. Yet the benefit is we get better information. We can make better decisions. Right. So for those that saw last month's presentation, this is a similar chart. It's also in the statistical tolerance analysis ebook, which is free up on Ascendo Reliability underneath ebooks, I believe. The idea here in how to run a Monte Carlo is pretty straightforward. The idea is, let's say I have three components, and one is actually a normal distribution, one is skewed, and one is, well, we expect it to be filtered or screened before it comes into our assembly, so we're going to call it a uniform distribution. The manufacturing process makes all kinds of dimensions. We pick the ones in this range, assuming, of course, that our measurement systems for the filtering are accurate. And let's say we're going to stack those three parts, right? We're just going to add their dimensions up to it. So what I do is I take a random component from this distribution, from this distribution, and from this distribution, and add them to this function, right? And this transfer function, this piece here, in this case would be the summation of those three parts. Now I'm not adding the variances here. I'm adding the actual randomly selected component dimension. If this distribution represents the range of variability possible that we're looking at, well, I take a random sample of these three distributions and I add them, right? So it'd be just a sum of these three components. And we'll do a little normal, skewed, and uniform. And add them up and I get my system thickness. Let's say these three plates, I get their thickness. And that becomes just one tally on this resulting histogram. And then I do it again. I take another part, another random sample, and tally them up and I get a component, and so on. I continue to do that like 10,000 times or whatever is appropriate for the accuracy of your analysis, and I end up getting a histogram that may or may not have a known distribution, but it's the culmination of many virtual constructions of what's possible given our understanding of the range of variability of the parts. And if this range, the resulting range, is within our specification of what we consider to be working for the design, we're good, right? It accounts for our best understanding of the range of variability, and it allows us to quickly understand what the resulting stacks will be. Now, underlying assumption is that we're accounting for all the sources of variability, of course, and it goes true with all of these types of analysis. But it also then allows us to say, well, here's our spec, or lower spec is right here. So this proportion, this lower tail proportion, is actually going to be out of spec and lead to either a yield failure in manufacturing or early life failure in the field. And so we can calculate that. And that's, to me, the advantage of both the Monte Carlo and the root sum squared, is we can do this kind of analysis to see what the downside is, given the range of variabilities we have. And with this kind of model, as we change assumptions about these distributions, we can see which one has the biggest impact on the result at the end. Now, naturally, the one with the largest range of variability, this uniform distribution goes over the entire range. It's equally likely to get it near one edge versus the center. Will probably have a pretty good impact on this. Can we improve that process? And how much do we need to improve it to improve our resulting assemblies' actual performance? So these kinds of analysis go beyond just putting plus or minus 10% on a drawing. It allows us to understand and incorporate the variability of those components going into the product. Our role as a reliability engineer is looking for those ranges of variability that impact the resulting performance in the field of these systems. And so being part of that discussion and part of that analysis allows us to influence that design during the design phase, that design for reliability aspect of what we do. And so that's why I keep coming back to tolerance analysis. Even though it's not our primary function, it has a significant lever on the resulting design and how well it performs in the field. And so for a much better example of Monte Carlo and how to do the examples, to see the statistical tolerance analysis ebook and or last month's webinar. When is it appropriate? When it's important, right? When, one, we have to have better data. If we're just making straight out guesses on all the data, use root sum squared. It's now, unless we really know it's not normally distributed, and we still need to come up with some estimate of these distributions. It also takes a bit more time to set up, to get the data, and run the analysis. Now, some CAD programs, I've learned over the last few years, have Monte Carlo built into it for doing tolerance analysis. You have to add the variability, right? And it allows you to run it pretty quick. So there are ways to do this pretty quickly. It's just a feature you need to encourage or enable to happen, and tie it to the reliability performance. You can also tie it to manufacturing yield, which is another usually big hitter for people involved with paying attention to the manufacturing process. So you can get some champions there. Now, our role, and this is a quick summary of what we do, is we know that the average or the mean is just not good enough, right? It's not good enough for life data analysis, and it's certainly not good enough for design and setting requirements. We also know that specifications are not the same thing as what's the range of variability we will experience, right? So for those elements that in your design team's experience and opinion, and or in our experience with working with prototypes, says, hey, this part, its variability is important, or this system, or this stack up, or this clearance, or whatever is important for the resulting performance of our system, well, then we just need to go get the data. We need to go get the best available information we can so we can do root sum squared and or Monte Carlo analysis. Now, always remember that if we're making measurements, that measurement error can really throw a wrench in this whole process. So make sure your measurements are not introducing another random variable that you don't need to deal with. So, Joe, your question, you can use raw measurements. You can just create a histogram, right, and draw randomly from that unnamed distribution, if you would like. A non-parametric is a good way to say it. If you know that it fits a particular distribution well, the algorithms for randomly selecting, say, from a log normal distribution are pretty quick and efficient. It's a little more difficult to pick from a non-parametric, from just a random histogram data set, but it's possible. Certainly is possible. It takes a little more setup to make it work. So our role as reliability professionals and reliability engineers is often focused on getting a good design, this design for reliability aspect of what we do. And so tolerancing is, in my opinion, a significant opportunity for us to influence the design to make it more manufacturable, more reliable, more available. And so it's where I would focus it. But it all comes back to variation. Is all too often I've run into designers that go, well, I don't know what the variation is, but I'm just going to use plus or minus 10%, and I'll do a worst case, and yeah, it's working. Now, I don't like being surprised with prototypes not working or with clearances not going together when I'm trying to assemble the first set of products on manufacturing. It's expensive. It's late in the game. We have to make quick decisions that are often not well thought through, and it often leads to more problems. If we pay attention to it early in the program, early in the process, and that's tolerancing, then we can influence a significant ability for the product to just work, right? And help that really occur. So you can call it design for reliability, you can say design for manufacturing, you can use whatever works for your organization to get involved with that. And then bring to the table the tools, the techniques, and an understanding of variation. So there's plenty of hurdles, right? Getting the data, getting the influence on the design team at that very early stage of the design process are two hurdles. Now, I'm sure you can think of a few more, and I'll look forward to what you suggest or what you see. But overall, the idea is that stuff varies, right? It's going to happen. Let's focus on those critical systems where that variability will impact the resulting reliability performance. Let's get the data and do the analysis. And that helps us then focus on what variability is okay and what variability we need to really focus on and either monitor and maintain or improve. And so it really spans a pretty wide range of stuff that we do and care about, but also really enforces our ability to influence the design. And so that's why I like tolerance analysis. So.